and welcome to the podcast of Loughborough University's Institute of Advanced Studies, a podcast where our international fellows discuss the most pressing issues of today that we're all facing and share their exciting research ideas. We hope you enjoy today's talk. Thank you for tuning in.
Thank you very much, Kiran. So a quick introduction. So Professor Saccomandi is an applied mathematician with a strong background in physics and engineering sciences. So he's currently a professor at the University of Perugia in Italy since 2007. And this follows his previous appointment at Sapienza University of Rome and the University of Salento. Professor Saccomandi's current research focuses on the axiomatic theory of continuum mechanics and wave propagation, with particular interest in modeling, describing, and predicting the mechanical behavior of rubber-like materials and soft materials, such as gels and biological tissues, for example, skin and brain. Professor Saccomandi integrates experimental data with rigorous mathematical modeling to improve predictive capability of the models. In addition to his academic positions, Professor Saccomandi also serves as director of the National Group of Mathematical Physics and a board member of the National Institute of Mathematics under the Italian Ministry of Scientific Research. He is co-editor-in-chief of the International Journal of Engineering Science and Applications in Engineering and contributing editor of the International Journal of Nonlinear Mechanics. One of the great continuum mechanics scientists of the 20th century, Gerard Mogen, in his book Continuum Mechanics through the 20th Century, noted that Professor Saccomandi's work is marked by a fruitful cooperation with foreign scientists, often in the British-Irish tradition of applied mathematics. And indeed, we have the pleasure of hosting Professor Saccomandi's visit to Loughborough University, and today he will give us a talk on constitutive modeling in nonlinear elasticity.
Thank you very much, Karima. I'm very grateful to Karima and to all the staff of the EAS for their support and the opportunity to be here in Loughborough, in this very beautiful campus, to spend this month to do research in the mathematics department. So thank you very much. Thank you very much to the staff. Thank you very much to Karima, and thank you very much to all of you that today you are following my seminar, that I hope it will be not very boring. I mean, I'm trying to do more interesting as I can. So what is the topic of my seminar is to speak about the mechanics of rubber-like materials and soft tissues. The idea is to find a good mathematical model to explain the mechanical behavior of such materials, and the problem we have to face in searching for this mathematical model is a little bit the following. The framework is very well known. We know what are the methods and the tools we have to use, but there is a bug, which is how we can find a strain energy function which is effective in predicting the mechanical behavior of such material, and this because we are in a nonlinear framework, and therefore there are many choices possible. This is the main problem. So how we can face this multiplicity of choice, and we can end up with something which is practical, which is careful, and which is therefore effective. Okay, my story will start from 1966. If we have time, we can make a sort of we can play with this all these kind of photos which are about 1966. But for the moment, I will only focus on this journal, which is the journal of the Italian Association of Mechanics and Theoretical and Applied Mechanics. This is a journal which is not a very interesting journal today, but when in 1966 the first issue comes out, it was quite important for the Italian scientific community because it was the first journal where Italian was obliged to write in English. And this was very important as driving force for making more international the Italian community. And in the first issue, page 15, there was this paper here about the thermodynamic potential for continuums with reversible transformation, some possible types by Giuseppe Grioli. Giuseppe Grioli was a very famous professor of rational mechanics in Italy. Many people has studied in his textbook that you can see here. He was based in Padua, and he was a student of Antonio Signorini, another very famous Italian man in mathematical physics. The interest of Grioli was mainly the dynamics of rigid bodies, what we denote as stereodynamics, and continuum mechanics. Now, what happens? That, I graduated from a very old university. The University of Perugia after Bologna, I think, is one of the first university in Italy. So it's very old. But from the point of view of mathematics, engineering was not so strong. But every year, Grioli comes to Perugia twice because the full professor in Perugia at this time of mechanics was a friend of him. And so I met him for several years, at least twice per year. I met that he was already quite old because he was already retired. And when he comes to Perugia, we stay for a couple of days very near because people interested in mechanics was 3-4 in all the universities. So we spent a lot of time together, and at this time there were no PDF, but there were reprints of papers, and one, he gave me this paper, and he explained why, in his opinion, the nonlinear theory of elasticity was a basic theory to learn if you want to do continuum mechanics, nonlinear continuum mechanics. In the idea of Grioli, the fact that it was a basic theory was mainly because all the key features of nonlinear elasticity are the basic key feature of all nonlinear continuum mechanics. So if you want to learn exactly all the strain measure, all the facts associated with some basic fact like framing difference or objectivity, in Grioli idea was to start from the nonlinear theory of elasticity. And at this time, there was not truly many application of the nonlinear theory of elasticity. Nowadays, we know that there are important applications in the soft tissue mechanics, so cardiac mechanics, brain tissue, soft tissue elastography, vascular mechanics, also in geophysics, but at this time it was not so clear still, and also the transition from the mesoscopic structure of such materials and the macroscopic was not known, was truly a new field of interest, but already Grioli was aware that also in this case, without all this important application, in the rheology and complex mechanical behavior of solid and fluids, you have a fact which is very important, for which it's clear that you have to know about the nonlinear theory of elasticity, and this fact is that the static theory of all this huge class of materials, behavior, is always collapsed to the nonlinear theory of elasticity. when I read the paper by Grioli, the paper I've shown you before, I was truly interested by this fact that at a certain moment, Grioli say, one of the most interesting problems in the mechanics of continuums with reversible transformation, so elastic materials, fit to a rubber band. You know? The rubber band may be easily deformed, and when you remove the reason because it is deformed, it comes at first sight exactly back to the reference configuration. Is that of the determination of the thermodynamic potential. And it presents two aspects. The physical one of collecting all the information from the experiment, and the mathematical one of the construction of this analytic expression compatible with the experimental indication. And he say, this latter are in general largely insufficient. The experimental indication don't allow you to find exactly the thermodynamic potential. Hence, the experimenter, in order to be able to work, must needs to presuppose a certain type of analytical structure. When I read this, I say, this is what I want to do. I want to use mathematics to go into this and to do this kind of research, to connect my knowledge of mathematics with the experimental data. And so for me, it was the beginning of a great interest and passion. Now, just a little bit of notation and mathematical ideas to may, because otherwise I cannot put in the right framework what I have to say. So I'm considering a reference configuration. You see this sort of big potatoes. And here I use capital letters to indicate every point, okay? And then deform, I have a current configuration, a deformed configuration, where I use small letters, and I have a map between the two configurations, which is written here. This is the map, okay? One of the major actor of the map is the gradient of deformation that you see there. Now, the gradient of deformation is important. Imagine when you do transformation to compute integrals, for example, if you need the Jacobian of transformation, and the Jacobian is just the determinant of this object, okay? But we use these quantities related to F because we have this idea of objectivity, which is very important. The fact that if I deform a material, or if I deform and rotate rigidly the material, the internal forces are the same. So I use this quantity, and associated to this quantity, you have some invariant quantities, which are the trace, the second moment, and the determinant. Invariant with respect to rotation again, okay? So to simplify, I will speak only of the case of isochoric deformation that preserves the volume, and therefore E3 is equal 1. And my potential, my strain energy density function, so all the constitutive information are in the choosing the potential of my material, which is a function only of E1 and E2 because I'm considering the isotropic materials, okay? This is exactly the same potential that you have when you study in classical mechanics and conservative force, okay? Exactly, but we are in a framework more complex than just the one of particles, because here we have bodies which may deform. We have not only particles that may move. Pay attention to this fact that this strain energy density function, this potential, is in reality the isothermal version of the free energy. For people who know something about thermodynamics, the free energy the Helmholtz free energy, which is just the internal energy minus the temperature, the absolute temperature times the entropy, okay? And this is clear if you have a little bit of knowledge of statistical mechanics. This is the internal energy, so the measure of the link among the various particles, and this is the entropy. And you see that in reality, a body what want to do, want to minimize the links and maximize the entropy. So you want to stay in much more states it's possible, okay? And this is just the isothermal version, but this squared, this boxed formula is important to recall in fuselage. And this is the Cauchy stress. The Cauchy stress is the way you can compute the internal forces, so the forces which give you the possibility to have a form and a volume, okay, to be a solid. And as you can see, there is this Lagrange multiplier, here P, which is associated by the fact that E3 is equal to 1, only isochoric deformation happens. And here you have the derivative of the strain energy density function with respect E1 and E2, okay? So the problem is what we can do to choose properly this quantity. Now, let me review, this is chronology, is just the Italian from, I apologize, from chronology, a little bit when I start to work, what was a little bit the situation in rubber mechanics and soft tissue. So I start from the 1927. This is just a date to say that before that, before this date, people working in rubber elasticity was very few. We know from the point of view of continuum mechanics, the balance equation, which works not only in the linear case, but also in the nonlinear case. There was some activity in nonlinear elasticity, but very episodic, okay? Very great names. I can remember Voigt, Reiner, I can, in Italy, Almanzi, and so on, but there was very few activity. In 1927, something happens in the USA. In Detroit, the Ford T model is no more production, and the Ford A model start the production. The Ford T model was sold in more than 50 millions of cars, okay? So what happens during this period? That you need in the USA more and more tires. And to make a tire, a single tire at this time, you need 7 kilos of raw rubber. And the only rubber you know at this time was natural rubber. So the importation of rubbers start to grow. And so the people start to think that was necessary to understand the mechanical behavior of this material. Okay, before that, rubber was used only for some waterproof shoes or things like that. So the mechanical behavior was not truly necessary to be understood. Okay, so what happens during this year? For example, in Boston at the MIT starts the first industrial project on rubber, okay, on rubber mechanics, and was Encke, the famous Encke, you know, a famous scientist which name is related, for example, with the Encke strain measure that drive this project before to come back in Europe, in Germany, and then to move to Russia. Very strange. He was German, Encke, then he go to Holland, then he go to the States, then he come back to Holland, and then he go to Russia. Very strange history. I mean, and but what was doing by Yankee was, in some sense, very trivial. It was just adapting the linear theory of elasticity, saying, we need some finite measure of strain. Okay, it was not doing truly a general new theory. It was just considering how to adapt the linear theory of elasticity. In the same time, some people in chemistry, people interested more in cooking the rubber, because you must know that the natural rubber is a very soft material. You have to vulcanize it with silicates to make it a robust material. They was doing some very basic theory using statistical mechanics, kinetic theory, taking into account the fact that at the mesoscopic level, you have that rubber is composed by macromolecules cross-linked by these silicates, these carbon black materials. In 1938, the British, that was the greatest producer of natural rubber at this time, with the Belgian. In Congo, there was many plants of natural rubber, Hevea brasiliensis plants, and also in Malaysia, but Malaysia was under the empire. Start the British Rubber Producer Research Association. So there was a research institute only for rubber, and the head of this institute was Treloar, the famous physicist who wrote the book, The Physics of Rubber Elasticity. Then in 1940, in the Journal of Applied Physics, you have the appearance of the Mooney-Rivlin material. In reality, this material, which still is quite used, was proposed by Mooney. As you can see, it's linear. C and D are just constant in the invariance. It's just a very simple model. But the paper of Mooney is very interesting, because it's one of the first papers where a rigorous approach is tried. In the sense, the hypotheses are clear, and from the hypothesis, the Mooney tried to find, to characterize a potential. Mooney was wrong. This was not the only potential which agree with the hypothesis do, but this was a very important point. In 1948, the first paper by Rivlin of 5 papers in the philosophical translation of the Royal Society starts what we say today, the modern theory of nonlinear continuum mechanics. Why? Because he started to use in a massive way linear algebra. So everything is modern. If you read the papers by Rivlin today, you feel that they are completely in our language. Maybe there is too much index notation. Today we prefer to use not always index notation, but everything is clear. Rivlin do much more than Mooney about that, and indeed he proposed a function, a general function of E2 minus 3, and not just a linear term. But at the end, when he do the computation, he use the Mooney material, and for this reason, everybody denote this material as the Mooney material. Then, in 1938, there was the Congress of Applied Mechanics in London. Okay, the Congress of Applied Mechanics was the today is called ICTAM. Okay, International Conference on Theoretical Applied Mechanics is the main conference that every 4 years has done by the UATM, the International Association of Applied and Theoretical Mechanics, and you see that they start a certain group, mainly in the UK, working in nonlinear elasticity. Breen, Zerna, Adkins, this was the name. But for many years, nothing happens, because at the end of the day, these models proposed they was very innovative, but they don't describe careful all the data, and therefore people was a little bit skeptic. But in 1972, you see there Ray Ogden proposed his very famous model that you can see there. And this model is proposed not using E1, E2, but remembering that E1, E2, and E3 may be rewritten in terms of the principal stretches. What are the principal stretches? Are the eigenvalues of the symmetric part in the polar decomposition on F. Every tensor by the polar decomposition may be written as a rotation plus a symmetric part. And the symmetric part, you can compute the real eigenvalues. And therefore, you can also express everything in lambda 1, lambda 2, lambda 3. In reality, there are many invariant sets, okay? All are in a one-to-one correspondence, but this was the choice by Ogden, and Ogden was the first one who described not so bad the data. In the same period, 1976, Ball was able to find a very interesting property to obtain for the Dirichlet problem the solution of elastic problems. Mathematician was interested in elasticity. Why? Because it's a variational theory. And so mathematician interested in calculus of variation was truly interested in the theory of elasticity as a possible application. And they was trying to find a good property of the potential from a mathematical point of view to have the existence of the solution. Clearly, if you have a convex strain energy, you have the solution, okay? But the solution is unique. And this was not in accordance with the experiments, because it's very simple to show you non-unique solution in nonlinear elasticity. It's very, very simple, okay? And for this reason, Ball derived a condition which is polyconvexity, which give you the existence of the minimizer sequence is to the variational problem, but not uniqueness, okay? The problem is polyconvexity was not truly clear what does it means at a mechanical point of view. So for many years there was a certain interest, but you know, things don't take off really. In 1993, Arruda Boyce proposed a model, which is the 8-chain model, which brings a connection, a clear connection in some sense, between the mesoscopic structure and the macroscopic. And this was important because there will start a convergence between people working in chemical physics and doing the kinetic theory and people working in continuum mechanics. In 1996, Alan Gent proposed this strange potential with the logarithm that don't seem very interesting. And you say, why I'm noticing that? Because you see that there you have a Taylor expansion, okay? But here you cannot have a Taylor expansion because you have when E1 minus 3 reach Gm a singularity, and you can never expand a function with a singularity in Taylor, okay? If you do that, you lose the singularity, and this was important. Then in 2000, Professor Gasser Ogden derived their model for arterial walls. And here it was the blow up of interest for nonlinear elasticity because everybody working in biomechanics and soft tissues of biomechanics want to learn that. In 2004, and here I'm starting, there is my paper with Ogden about his model, which start a new chapter, as we will see soon.
Excuse me.
Yeah.
In the previous slide, in this logarithm
Yeah,
formula,
yeah.
where is I2?
There is no I2. There is. It was only function of U1. Clearly, you can also have. You can take D equals 0. Okay. This is a subclass.
Gm is constant.
Yeah, yeah. And what happens then? Okay, I told you that Grioli was old. He was already retired. He was not active. Then I start to work in truly in this field, thanks to my case. Okay, that was the first PhD student of Rivlin. My relationship with my case has been very deep, and my case introduced me, as Karima say, that Mogen say, in this British-Irish tradition of applied mathematics. And it was great to work with him, but there was a problem for many years, that I start to work on universal solution and relation. What does it mean, universal? There was this idea that there was some results that works for any choice of the strain energy density function. Okay? And Trussell was the first one to say, oh, these are the important results. You have not to restrict to any special form of strain energy density, of potential. You have to do that. Every result must be general, must work for every choice. And this was important. For example, the universal solution, which does not depend the geometry of this map does not depend on the potential, are fundamental in doing experimental research. Because if this map depends on the strain energy potential, when you deform the body to understand the behavior of the body, the geometry depends on what you want to measure. And then you have a loop which doesn't work. So I do many interesting things for 10 years, but when I met Alan Gent, the man of the strain energy with the log, I understand that the situation was completely different. What was truly the need of the application. Alan Gent was a student of Rivlin himself, but then he moved and he was the Goodyear professor in Akron, Ohio. So he was very applied, but he was able to speak the language of continuum mechanics because he grew up with this language. So he explained me that the problem was to the data. You have to not to consider a universal solution or universal relation. You have to go through the data because we need that. We need to describe the data and to make prediction. So he boosts me in working on data, and then he give me the famous Trello data that was a sort of gold benchmark. Okay, and here you can see here the data. This is the stretch, and this is the stress. Okay, for the uniaxial extension. Uniaxial extension is the basic, very simple experiment you can do. You take a rubber band, okay, you hang the rubber band, you use a weight on the other extremum, and you look what happens. And as you can see, you have a stretch that can reach near 8. This means a deformation of 800%. So you can see, and with not a very large amount of forces, the Young modulus of rubber is 100 megapascal. The Young modulus of metals is of the order of gigapascal. So you can, this is the reason because you can stretch a lot a rubber band just using your hand. You have not to be Iron Man to do that. No, it's clear that what Alan Gent told me first, he say, look, if you take this data, okay, of Troller, and you contrast this data with all the models that have been proposed, you will see that there are huge relative errors, and nobody talk of that. Then I start to work with a modification of the Gent material, which is written here, and now you have also E2. And what I obtain these fittings of the various parameters, these fittings here. And as you can see, the relative errors are very low, are less than 3.5%. Here I have another kind of data, which are not the Trello, because the Trello was data taken during the 40s, okay? So the device to take this data. So I take some data by Carrillo, Dobrin and Carrillo, which has been done with better devices in the 80s. And as you can see also in this case, I have very low relative errors with this model. Now, I'm not presenting this model because I want to say I was very good, I found the model. No, I'm presenting this model for two reasons. That the first reason is that you see here we have only three constitutive parameters, C, D, and Jm, okay? If I want to do something similar with Ogden model, I need 8 parameters. So I say, but this is very strange. Everybody say that the Ogden model is so powerful, so interesting, but you need a lot of parameters. So there may be some overfitting problem there, no? And indeed, in 2004, I start to work with Ray Ogden in this model, and we discover a very strange phenomenon that to obtain the same kind of relative errors, I have to take a parameter. R has to go to 4, okay? So 4 pieces, and you obtain that if R is equal 4, you have a multiplicity of optimal set of parameters. This means that I can find several sets of mu R and alpha R, which have the same descriptive power, but they are different. Okay, we have a multiplicity. Why? Because when you do the fitting, the objective function of the fitting is not convex anymore in the alpha R, in the exponent. It's a nonlinear fitting, and is not convex, and then you have no uniqueness. The problem is that for any set of optimal parameters, which describe at the same level the data, you have a different predictive model. If I do a computation with one set of another one, I obtain different results. And this is a disaster. There was no way to escalate some set of parameters. By the fitting was not possible. There was all equivalent from a predictive point of view. By thermodynamic reason, there was all admissible. So it was a disaster in some sense. Moreover, it was very hard to link this to the mesoscopic structure of rubber. But we will see that on the other end, this JM is clearly related to the mesoscopic structure of rubber. This was a little bit a shock for Ray, but also for me. And in the same period, I read the obituary of all of Clifford Truesdale, and Ball say, he's saying that it's Ball that has resolved the problem of the well-postedness of boundary Welle problems in nonlinear elasticity with his Pauling convexity, but he said that at the end of the day, perhaps he would have been realized that Hadamard notion of well-postedness, in mathematics, Hadamard notion means that when you have a boundary problem, you must have existence, uniqueness, and continuity with respect of the parameters, stability. Is too restrictive in the nonlinear setting. For example, non-uniqueness is clearly not real. You can do you can take a credit card and you see that sometimes the credit card, if you compress, go this way, sometimes in the other ways. And you see that non-uniqueness is not there. and have a non-existence comprise acceptable behavior, and that there are probably no fundamental restriction of the strain energy function at all besides those arising from material symmetry and from indifference. So he say there is no solution of the problem. Okay, and indeed in this period, I for a moment I was believing. You see, you know what is that? Someone recognized this picture somewhere. It's very famous in the UK in reality. Yeah? In Manchester, is very, very famous. This is from a cemetery in Genoa, in Italy, Staglieno, where Peter Hamill has taken all the cover of the long playing by Joy Division. I don't know if you know Joy Division. It was a very famous band in Manchester in the 80s. And okay, but it was truly a disaster. But there was something strange around that don't stop me to continue to work on this. Is look here, this is the number of paper about nonlinear elasticity. And as you can see, this is Rivlin, then flat, Ogden, ball, then start to go back, but after the Holzpfeffer Gasser Ogden, there was a blow up. So it was a moment after with the new millennium that to work in elasticity was truly very actual. And then I don't stop. And I start to understand that I can solve the problem only using a multiscale modeling approach. And where they comes the multiscale approach? It comes from here, from the thermodynamics. We have, and this Grioli was truly innovative in thinking that the problem was a thermodynamical problem and not just to choose a potential like that. And here you have to go to the structure of the rubber to understand how you can obtain a solution. So you know what is rubber is. This is a cartoon. Is just a polymeric network. You have macromolecules that are cross-linked together. If there was no cross-link, rubber would be just a liquid. And there is the cross-link and then is a solid. But clearly, in such a way, it's very easy to deform it because there is no strong links, okay? And how you can go from this mesoscopic structure to a macroscopic model. First of all, you have to have the model of a single chain, okay? You have to say what is a single chain and why there is a reference length for the single chain. There is a reference length for the single chain just because it's highly probable among all the possible lengths. Okay? And if I start to stretch, I need forces because it's less probable. And indeed, if you stretch at the maximum the chain, there is only one configuration that can satisfy that. And then I need a lot of force, an infinite force. Remember that, an infinite force. And then once that I have the chain, I have to do an average on all the chain for all the network. And how can I do that? I can imagine to have some building blocks. For example, like Arrudabos do, an 8 chain. You have a cube, you have 8 chain, you have a model for each chain, and then you can average, you have a model for the cube, and then you can average like the macroscopic, the polymeric network is given by many cube. Moreover, this fact to have the cube is very easy to connect the macroscopic deformation to the microscopic because the cube is the infinitesimal element. And then F acts on the single cube. No, because this is F is an infinitesimal quantity. So this was the idea, and the idea was to neglect this to do the entropic part of elasticity as people working in kinetic theory, and considering that this was the main contribution, the entropic one. And people in kinetic theory was also able to have a measure of that and to see that this was a second order effect. So it was nearly done, but something missing. We have again to have a way to go from the microscopic length of the chain to the macroscopic. And this was this man to give me the idea. You see, these are three famous rheologists. This is Zappas, this is Bechten, and this is Kearsley. They are the famous rheologists of the KBZ fluid. I don't know if you know, that is a very famous model in non-Newtonian fluid mechanics. Okay? And once I met Bechten, and Bechten, I talked with him of my problem. He said, oh, but there is a very famous result by my friend Kearsley, stating that the first invariant, this one, okay, is equal to 3 times the square of the stretch ratio of an infinitesimal line element averaged over all possible orientation in space. So he said, it's very simple then. If you have the ratio of the current length of the chain to the extended length, no, which is the measure of the stretch of the single chain, you can go by this result to find that this is the relationship is just the square, okay, of excuse me, the square root, because this was the square in this or 3 times, okay, you go there, and n is the maximum length of your chain. And then if I consider, okay, if I consider the kinetic theory experiments and models, I go to this form of the stress, where, for example, this beta may be the inverse Langevin function. Okay, this is the Langevin function. Okay, but with this, I go back to look what happens from a macroscopic point of view. And look here, this is the strain by jet, the strain energy function. This is therefore my stress-strain relationship. Here I use the Kearsley to go there. And what is the relationship with before? Look at the inverse Langevin function. You see I have only rotate to have the inverse. Look here from 0 to 1. You have a singularity, you see? And this is exactly this singularity here. And indeed, if I do the Pade approximation of my inverse Langevin function, I go back there. So what does it mean, the Pade approximation? If I have a function, I can do the Taylor approximation, but I lose all the singularities. Here I have a singularity which is central, because I have to predict that when I approach the final length, the forces has to blow up. And to do then an approximation of this function, I have to use a rational function, ratio of polynomial. And as here, you see, this is a first order polynomial, this is a first order polynomial, okay? And if I do the Pade approximation of this function, I obtain exactly the Gent model. And Gent was not aware of all that. He was just imagining, just by intuition. But this gives me a very interesting framework that you can find in this paper declared that we need rational function, no Taylor expansion as Ogden and Rivlin was suggesting, that we need compatibility, full compatibility with the linear weakly nonlinear theory. Now, I don't discuss this point. And as was pointed, we need E2. Why we need E2? Because I go back to my previous work on universal relation. If there is no E2, when you shear a piece of, this is a piece of pig brain, shearing it, it cannot move in this direction. And we see in all the experiment, and this does not depend on the strain energy, that, and you can do easily by have an hole on the machine, that in reality you are pumping in this direction, the material. If you do this with the correspondence by Bicursively, the rational function, and some other condition, you go to obtain a good model. And moreover, once that you have understood how you can do going from the micro to the macro, you can do much more interesting situation. For example, you can do things that take into account the damage of the network. So some chain can break up, some chain can heal. You can do that putting inside probabilistic or statistical mechanics consideration. And there is a completely general framework now to go from one to the other by just decomposing F in a part which is material that change the reference configuration, and in a part which is just elastic as before. So you have an elastic part and a part which may be plastic or what you want, okay? Now you have all the ingredients to do that, okay? And what happens more recently? More recently, it's happens something strange to me, because Truesdell always was a very important scientist in the last century, but he was always very strong. And then I think he gives some indication that sometimes was starting to be a sort of prejudice. When you use invariance, I told you that invariance, any symmetric choice of lambda 1, lambda 2, lambda 3 gives an invariant. These are some symmetric choice, but you can change the symmetric choice. There are many. And then Truesdell says it's important to realize that since h of several material tensor is an isotropic function of any one of the other, an exact description of strain in terms of any one is equivalent to a description in terms of any other. And this was my belief. I say, okay, I use E1, E2, E3 because all the other are equivalent. Okay, then I forgot to read what was after that. Only when an approximation is to be made, may the choice of a particular measure become important. So what we are doing now is to choose to do a special choice of the strain energy, okay? And therefore, to use this invariance with alpha equal to 2, when it is incompressible, I must say something, that when it is incompressible, E2 is equivalent to lambda 1 minus 2 plus lambda 2 minus 2 plus lambda 3 minus 2. When this is equal to 1, you can do the computation and to find out. So to use alpha equal 2 was only a possibility. Why we have to use alpha equal to? Why we have to do like Mooney and Rivlin used to do? And at a certain moment, I found a universal relation which depends only on alpha, not on the form of the strain energy. And for example, if you consider the pure shear deformation, which is a spatial plane deformation, this is the universal relation. These are the stress that the forces stress associated to the force you apply on this piece of rubber in the orthogonal direction, and this is alpha, and this is the lambda. And when you do a comparison with the data, you see that you never obtain alpha equal 2, but you obtain other values of alpha. And this is also, if you go back to the cursory results, where you do the isotropic average, this is also connected to this fact that is not true that when you are stretching a material, the isotropic average is a good description of what happens in a microscopic case. Because when you are stretching a materials, in one direction you are stretching, but by incompressibility in the other direction you are compressing. So to do this average is not truly smart. And if you take alpha different from 2, you see that you are doing a first correction in the other direction of this kind of an isotropic behavior. And then what we have tried to do is to look at this material, which is the case, in the case alpha equal 2, is just the Muni-Rivlin material. But for other alpha is another kind of material, but always linear in this invariance, generalized invariant. And you see the results here. If you take Muni-Rivlin, which is the red one, you don't obtain good fittings like if you obtain, for example, alpha equal 3, and you can see here in the relative level. Okay, so I think it's time to stop, and I've done something wrong. No, okay, there was and I stop here saying that clearly we are not today, we don't know exactly what is the potential. But we have more experience and better idea than 20 years ago. Because 20 years ago, there was a truly a naive benchmarking against experimental data. And today, we are able to use better statistical ideas to compare the data. 20 years ago, we were sure that we need just Taylor expansion, but today we know that we need more than Taylor expansion, okay? And there was completely a lack of awareness regarding the impulsedness on the parameter estimation. And today, we know how to work with that, with for example, the universal relation. There is a point of view which is driven by multiscale and multi-physical understanding, and this gives a stronger link with experimental application. So many questions have been answered, many more we have to reach, but we can say we are a little bit half in the woods. So I will stop here, and I will thank you for your keenness in listening to me, and I hope that this talk was helpful to describe what I have done and what we have done, many in reality, as my workers and as other groups in this direction and in this topic. Thank you very much.
Thank you for listening to the podcast of Loughborough University's Institute of Advanced Studies. A quick reminder about how to stay connected. You can find us on Blue Sky, LinkedIn, and Instagram, and you can also watch the presentations on YouTube. The podcast is available on all the major platforms. Please download, share, and most importantly, subscribe. See you next time.